Hi there guys, well welcome back. We've just done 5C, we're about to work on 5D, and 5D is all about analyzing histograms. So it's comparing histograms, it's drawing histograms in different ways, it's reorganizing the data a bit, it's looking at the distributions from histograms, and it's looking at relative frequency towards the end as well. Okay, so again, there's going to be a bit of chat here. There might be some things that you should note down and create some notes as I'm going through these ones, but because it's a bit more graphical, it's kind of it's quite, I think this is a little bit nicer than the previous exercise. A little bit here about the origin of the word histogram. It says it originates from ancient Greece. Histos means stand upright, and gram means a drawing. There we go. English mathematician Carl Pearson and eugenicist was the first to use this word. Okay, there you go. So here we go. Hang on a second. We've got here talking about the distribution to start off with. Okay, so we've got CSOS. Maybe this helps you remember ways in which we can talk about the distribution of a histogram or distribution of data. So CSOS, we'll see this in one of the questions later on. It says, look for the center, look for the mean, the median, or the mode. And that may be obvious from your histogram. And look for the spread. What about the range? What about the maximum? What about the minimum? What can you see from your histogram? We're trying to take a graph. There's going to be some graphs in a second. And we're saying, well, how can we describe the distribution of the data here? Well, we can look at the center, we can look at the spread, we can also see if there's any outliers in the data. Is there anything which is extreme? And I think this one pops up later on, but there's a definition for outlier here. And the definition is to be, let's just steal this one here, okay? Just take this. And it says that a data item is more than 1.5 times by the interquartile range, above the upper quartile. Sorry, needed to finish that sentence. There we go. So some of you might be aware of these things. This, my attempt at drawing out a box and whisker plot, or what some people just call a box plot. Okay, and these will turn up later as well. Normally there's a dotted line in the middle. Sometimes it's a solid line. And this is just saying, well, here's our lowest value. So I don't know, maybe x1 if our values are ordered. Here's xn, our highest value in the population or the sample, depending on what we're dealing with, probably sample. And here we've got the median. So this is our median. And here we'll plot the lower quartile, and on the other end, we'll plot the upper quartile. Okay, so my point about this is just to talk about what this, to unpack this formula a little bit, but also to say that this comes from cumulative frequency graphs. And again, if you've done cumulative frequency graphs, then you can get out your median really quickly. You can get out your lower quartile really quickly. 3/4 of the way through your upper quartile, and often you can plot your lowest value and your highest value in that range, and then you can come up with this little graph, box and whisker plot underneath as well. Okay, if you don't know what I'm talking about here, this is going to turn up later, so don't worry about that. But some people may have seen that before, so it's just a reminder. So says the outlier is defined as a data item which is more than 1.5 times the interquartile range. Well, interquartile range here is this distance here. So if this distance here, I don't know, let's say this is 10, then if we are more than 15 above here, okay, if this is more than 15 above this point here, the upper quartile, or if this value is more than 15 below the lower quartile, okay, when we're looking at this, then those are considered to be outliers. So they're rogue values. They don't fit within the distribution. Now, that's just a definition. Somebody obviously just came up with that. You could change this 1.5 to 1.4 or 1.6, but it's just, there is a definition behind an outlier. This is the generally accepted definition. Okay, so the other thing which helps us talk about the distribution is its shape, and we can say that, for example, the shape might be skewed, it might be unimodal, or just have a singular mode, or it could be bimodal, or it could be multimodal, and we'll see that in the questions coming as well. Now, remember, I said this last time around. You may have skipped through some of my last video. Sorry about how long that went on. So positive skew is like this. You know, it's where we say, well, look, if here's our frequency here, and these are our this is X, the thing that we're interested in, the variable which we're interested in. If we've got things kind of loaded towards the F axis there, if our frequencies are nearer the start than nearer than the end of our domain, then we can say that we have a positive skew. And of course, you're doing it the other way around, and we can say it's going to be a negative skew. It's going in the positive X direction. Okay, so that's a little confusing perhaps, but there you go. So let's have a look at the shapes of the graphs. Well, there we go. We can see unimodal, singular mode. There's just one high point. Bimodal. Okay. Well, a distribution can be seen to be bimodal when you've got these two peaks. Now, that's a little bit different to when we've got just our set of data, because, you know, if we have a set of data, I don't know, 2, 2, 2, 3, 4, 4, then we say, well, there's one mode. Mode is this, it's 2. And 4 isn't a mode because there's 3 of these and there's only 2 of these. Now, when you look at that graph, you're looking at that and thinking, hang on a second, there's not as many in the category that goes from here to here as there is in the category that goes from here to here. However, when we're looking at just a list of data, it's easy to pick out the most common number which turns up, the most frequent number. But when we can see the distribution, we can say, oh, well, we can definitely see that there's 2 peaks. So it's also true to say that this is bimodal. You know, so if I said 2, 2, 2, 3, 4, 4, 4, definitely say, well, that's bimodal, it's got 2 modes. When we cross this off, we can only really say it's got 1 mode from the data, but from the distribution, we can clearly see that there's enough information to see that there's a pattern of 2 peaks. So we can say it's bimodal. Okay, and then you've got multimodal there, and you've got skewed there. That's positive skew on that one as well. Talked about that. Okay. It says, when you are comparing 2 distributions, it is important to be concise and clear in your description of the distribution. Use words such as wider, narrower, more varied, less varied. You can make estimates for the mean, median, or mode if they cannot be calculated directly. Okay, well, we can do that in this question perhaps. So this question split over 2 pages, but it's going to say, state the median class, state the range, comment on the distribution of the data, estimate the mean. Okay, right. So I'll go through those as I go through this thing here. So first of all, it wants the median class. What's it all about, by the way? It's talking about a histogram. Okay, showing the length of 51 fish caught in the river Avon. Oh, that word, Avon means river in Celtic, I think. So it's river. Okay, that's some obscure knowledge. Okay, so consider the following frequency histogram, and the question is for part A, what's the median class? Well, the median class is going to be where the middle fish turns up. Now, what's the middle fish? Okay, so we've got 52 plus 1 divided by 2. That's where the middle fish is going to turn up. So that's where the median is going to be. So, sorry, not 52, 51. I've done my calculation already. The 52 divided by 2, so we're looking at our 26th value. Now we've got 2, 3, 5, 7, 11 there. So cumulatively, that's 2, 5. Okay, so I'm just doing a running total here. So that's me doing 2 plus 3 plus 5 is 10. plus 7 is 17, plus 11 is 28. Okay, so the median is going to be towards the end of this class, but that's going to be the median class in this case. Okay, so we had to find out where our middle term was. Just check that with the book because, yeah, it's looking for the 26th data point. Yeah, it's doing the same thing. Okay, next thing is state the range. So state the range. Well, the range is potentially a maximum of 120, take away 20. It's possible that there's a fish here of size 20. It's possible that there's a fish here of size 120. I think. I mean, it depends on what the table looks like. I mean, if you're saying X is, up to 20 there, then 20 can be included. But then, for this one, sorry, it's the wrong way around. If I'm saying, 20 is included at the start and not at the end, then we couldn't actually include 20. We could include 20 in here. But we couldn't include 120 in here. But to be honest, we're talking about continuous data here, so we really shouldn't overthink this one. The fact is that this includes 29.9999. And so for our purposes, we can say that the difference between these is simply 120 take away 20. Anyway, that's the maximum range because, of course, the biggest fish won't necessarily be at the end of this category. Likewise, the smallest fish won't necessarily be at the start of the first category. So what do they say? Oh, they just say the range is 100. I don't think it is. I think the range, interesting. And you see how this statistic throws up these kind of issues, and you can always kind of analyze things further. But, you've got 120 and 20 there is the maximum range. So the maximum range that we have is 100, but the minimum range that we have is that these two fish in here could be towards 30. Let's say they're actually at 30. And let's say that this one fish here is actually at 110. We can do 110, take away 30, which is going to give us 80. So all I can really say is that the range is between 80 and 110 for the actual data, for the actual 51 fish. Now, in terms of the actual population, because this is only the sample, then probably it's bigger than that. Probably you're going to get some fish which are smaller, and you might even get a couple of fish which are bigger. But we definitely know that the range is going to be bigger than 80 for the population range. Okay, so we've kind of overthought that one a bit. But, it's sort of better to discuss those points than not. So C says the center. So this is where it's doing CSOS. How do you want to describe the distribution? Maybe you can remember that. So let's see if we can remember it. We've got CSOS. C is for central value. So our central value here could be the mean, median, or mode. Well, mode is going to be in this category, is going to be here. So we could say quite simply that the modal class is for the fish between 60 and 70 centimeters long. So that's the modal class. And that's going to be a quick way of talking about a measure of the center. Okay, now you can work out the mean from this, but I think that's coming up next, so I'll deal with that next. And again, we could also talk about the median here as well. And the median is, I think we said also in this category here, this is the median class. Okay, S, what does S stand for? Spread, I think, the spread. Okay, so the spread of these values here is between 20 and 120. So we can talk about the range. And we can also, if we're describing the distribution, it's perhaps even better to talk about the lowest value and the highest value, because that gives us more information than just the range. The range just says, okay, we've got 100 centimeters as our maximum range here. But if we actually say, but 120 is our highest value and 20 is our lowest value, that actually gives us a real grounding as to where the distribution starts and stops. So it's okay to say that. O was for outliers, and I don't think there's any outliers here, but I can't really know unless I've got my lower quartile and my upper quartile. But it doesn't appear to be the case that there's any outliers. It seems to be a relatively even distribution. Okay, it's kind of bimodal, but you know, it doesn't seem like there's any kind of extreme cases over here. There's not something over here. So I think it doesn't seem like there's outliers. Okay, doesn't seem, question mark. And for S, in terms of the shape of this, I mean, it's relatively uniform, but it would appear that it's bimodal as well. But perhaps, although it appears that it's bimodal, there's not an awful lot of data. So really we should collect more data to see if we can actually catch some more fish which are in this category here. It's quite possible that it's really like this. Okay, and we've just been kind of unlucky to not catch these because we're only talking about 51 fish. So, and you know, maybe bimodal. What does the S stand for again? For shape, okay. So this is like maybe bimodal. But again, you can comment on how bimodal. What are they saying? Yes, yeah, okay, they're saying the distribution is bimodal. They're just going with that. Okay, so you can too. Okay. So part D, there's another part to this, was there? Oh, estimate the mean. Okay, so this is kind of nice. You can think about how you'd estimate the mean here, but essentially you just need to make a table first. Once you've got a table, pretty easy. You know, we've got X between 20 and 30, and quite frankly, I don't know which end is going to be equals to it. And I think normally it's the top end. Let's see what they've got in their table. Right. Well, they've ignored that issue. Okay, by coming up with this on an Excel spreadsheet by the looks of things, or maybe the GDC. Okay, so you know the first category is from 20 to 30. The next category is from 30 to 40, and then we've got a midpoint. Okay, hopefully you've seen this before for mean from a table. If you haven't, you know, you can Google mean from a table. Okay, and so you've got your midpoints, which are 25, 35, and so on. And then you've got your frequencies here. And then, of course, you know, in that first category, you've got 2 there. So the 2 fish here add in total 50 centimeters to our total length of all the fish if we put them end to end. Okay, so, you know we've got 51 fish. So the sum of all of our frequencies should equal to 51. And when you do all your products here, so 25 times 2 plus 35 times 3 and so on. Once you've got all of that, you're going to divide by 51. And that's going to give you your estimate for your mean. It's an estimate because we've lost the original values. By putting these things in a table, we don't really know what the original values of our fish were by putting things in this graph or by putting things in this table. So, you know, maybe, like I said before, maybe these 2 fish here were actually really close to 30. So we shouldn't have used 25. Okay, so it's an estimate for the mean because we're having to use group frequencies. If you just have discrete values here, then you just end up with the actual mean instead. Okay, well, try this out on your GDC. It's pretty easy to put your data in. You can see on this one here, you know, if you go to your spreadsheets, maybe the first time you're using your spreadsheets, if you put in your midpoints, if you put in your frequencies, and then you go to, you know, analyze statistics or whatever it is in the menu, you can say, now put my statistics in column C. Now, when you're doing that, different calculators are different, but in the TI and Expire, you have to say, you know, for this first column, let's copy this. Okay. So you can see you get a whole load of data out here, and it's going to put your data in here and here. You have to choose that. But basically, although you can rename these things, if you don't bother renaming these things, and you can just define your column to be this when it comes to the finding where to find the X values, if you like, and you can say, it's pretty straightforward on the calculator. You need to say B with these square brackets defines this column here. So you don't really need to name things. You can just say, look, X is in this, B is in this, and you do need to use the square brackets. And then it will ask you, where do you want your results to go? And you'll say, I want them to go in C, close brackets, and it will start putting things in here. And you're going to do your one variable statistics because there's only one variable here. It's only X, which is changing. Okay, you can see it's got lots of things here. It's doing sum of X. It's got N. If you do sum of X divided by 51, that's going to give you your mean. So there's other things here which are useful, like sum of X squared. That's going to be useful for working out the variance later. And interestingly, we've got the standard deviation here, and this S is going to be the population standard deviation as well. So there we go. There's that will say n-1 there. So that's when we talk about an unbiased estimator later on, which gets quite difficult. Okay, you can see there's more information here, and check it out. They give you Q1 and they give you Q3. So all the worrying we did about this thing here, 3/4 of n plus 1 value to find the upper quartile, okay, or what they're calling their Q3. Okay, all of the concern about this and trying to find that from your list of numbers, actually, if you type in your list of numbers, or if you type in a table into your calculator, it will just give you out your quartiles. Okay, right, well, there you go. There's a bit of that. There's a graph there as well. There's the mean. Let's see how much more we've got to do with this. A little bit more. We're comparing histograms now, I think. Okay. Right, just let me have a sip of my tea before it gets cold. Okay. So, comparing histograms. So, it's interesting to note that if we choose different class widths, and they're talking here about eggs measured to the nearest gram. Now, if we've got different class widths, if we decide to have very narrow class widths, size 1 here, I believe, then you can see the distribution is less clear to see. If you have really wide class widths, then you can see there's a much clearer pattern happening. Okay, and there's not multiple modes, there's just a very even distribution. Now, if we go somewhere in between those two things, we can see now that the distribution doesn't look as even. So it really matters how we divide our data up. And, you know, sometimes it matters about the point you're trying to make as well. I mean, you can make statistics kind of say what you want it to say. What's the famous quote? The famous quote is lies, lies, and damn lies, or something like that. Lies, lies, damn statistics is the quote. Who said that? The phrase derives from the full sentence. There are three kinds of lies: lies, lies, damned lies, and statistics. Okay. It was Mark Twain. Okay. So this was popularized in the United States by Mark Twain and others, who mistakenly attributed it to the British Prime Minister Benjamin Disraeli. Okay. So yeah, you know, sometimes you can make statistics say what you want to say. You know, by looking at these charts, you can say, look, very even distribution. Or you change your categories and you can say, you know, actually, there's something really strange going on around the median weight. You know, there's something strange going in the center. It's just like there's a lot of eggs around the center, and then there's this kind of strange flat distribution either side. Maybe, frankly, that you want to take a bigger sample here to really find out more. Okay, so there you go. Okay, now let's talking about comparing a couple of distributions here, and you know you can compare these two here. This is more fish in the River Avon and fish in the River Blythe. Ooh, where's the River Blythe? Could be in Suffolk. Let's have a look at this one. River Blythe. River Blythe. Okay, let's check this one out. Oh no, it's near Birmingham. Okay, so there we go. Goes through the Midlands and Warwickshire. Okay, well, it's not actually showing it there, but you know, appears to be going near the NEC. Okay, sorry, just diversion. Okay, why have let's what is it saying? What are the visual differences between these two things? What does this difference tell you about the samples that were taken? Maybe it looks like there's more samples that were taken for the River Blythe, potentially. What are the differences? The first one looks to be bimodal. Why might you consider this not to be an important comparison about the distribution of the fish lengths in each river? Let's see what they're saying. It is very difficult to make fair comparisons between the data if the number of data points in each set is different. Okay, that's where they're going. But yeah, it seems to be that there's more fish in River Blythe that they've taken in the sample. So you know, it's saying that there's, oh, of course, because the axis is very different. Yeah. And now is that good enough to say there's more fish in the River Blythe? I mean, it's just possible that it's just a bigger sample. Okay, so in order to compare distributions, it would be good to use a relative frequency histogram. So we're still not going on to histograms which have unequal class widths. We are now looking at relative frequencies, and essentially what we're talking about here is let's find what percentage is in each of the groups, or actually they're talking about relative frequency as a fraction. What fraction or what proportion, or in brackets, what percentage of the data is in each of the classes or categories. So in order to do that, you just need to do f divided by n. Now, if you do that with this data here, and I'm obviously not going to do it myself, and you can see they've changed the data into its relative frequencies and check that they sum to 1, so that they give you 100% in each of the categories, and then draw your graphs. Now that would be a difficult exam question to give you because we're given limited time in an exam, but you should definitely know about what relative frequency is. And now you can see that 20% of the fish in River Chipping are between 30 and 40 centimeters long, and 20% of the fish in River Dure are between 40 and 50 centimeters long. Okay, and what does it want us to do? It says then compare the distribution of fish lengths in the two rivers. Well, it seems that perhaps in the River Dere they're more evenly distributed there, and it would appear that in the River Chipping it's potentially bimodal. You know, arguably bimodal, but definitely it seems to be that there's a lot of fish in the smaller category, and then there tends to be quite a lot of fish as well near the sort of 100 centimeter category too. So there seems to be maybe two populations of fish there, or two different populations of fish, whereas there seems to be a more homogeneous population of fish in the River Dere. Okay, what are they saying? They're saying from the relative frequency histograms, it is evident to see that River Chipping is more uniformly distributed. So they're not saying much at all. Okay, so 5D. There we go. You've got 5 questions there, no, 6 questions. And next time around, we're talking about good old-fashioned histograms with unequal class widths, which is what a lot of people would have understood histograms to be from GCSE or previous courses. So up until now, it's kind of interesting that we've allowed histograms to use frequency on the vertical axis, and then now we're going to be using frequency density on that vertical axis instead. Okay, guys, well, thanks for listening. Good luck with the exercise, and I hope to see you back next time. Hi there, guys. Well, welcome back, or rather, hello again. We have just done 5D, and I was saying that 5E is all about histograms with unequal class widths. And there's normally a little correction that you can make here by talking about frequency density rather than plotting a height of the frequency. Now, actually, the reason why I'm appending this on the end, there's really not much here at all. They're just saying, well, is it fair if you have unequal class widths? So, you know, they're taking an example here. Let's zoom in. I don't know what this is. What are we talking about? Weights of something or other. Okay, well, anyway, weights of something or other here are being plotted like this. And they're saying, well, is this fair? You know, is this a fair? Does this show the distribution? Because we're just plotting the frequencies, the frequency of each of the category. And it looks like it's a pretty even, uniform distribution, a little spike in the middle there. But when you think that, in fact, the categories are of unequal width, it seems to be unfair because they're much more likely to catch more if they've got a larger width. So, for example, between 0 and 30 kilograms is much wider than between 55 and 57 kilograms. So you can see there's actually the distribution is much more is much more kind of an even distribution with a mode in the center, maybe even more like a normal distribution. But the fact that they've got wider categories at the end makes it look like a kind of uniform distribution, just completely flat. So obviously this is not fair. This is not showing the distribution properly. And so the correction that you would do is you would divide all of your frequencies by the class width. So now you'd have your frequency per kilogram across that axis. So, you know, what's your frequency for the first kilogram? What's your frequency for the second one between 1 and 2 kilograms? And that way you're getting a much better picture of what's going on. Now, obviously you can't break down that first category into 30 different strips. So it's sufficient to just say 10 divided by 30 and just plot the height of that. And that will really lower it down. But the problem is then you'll end up with really small numbers. So 10 divided by 30 is going to give you a third. So you end up with frequency densities being really small. And the other problem with that is that then you have to undo that to get back to the frequencies. So you'll need to times by the class width to get back to the frequencies. Now, this is a lot of chat, and you know the truth is they're not actually asking you to do that. That's turned up in previous courses, but it's not turning up in this course. It's just a discussion point. So you know, if we have a look online at some of these, you know, there's like a GCSE question or something from Maths Watch, I think. So you can see this one, what they're doing there. Let's see if we can open this one up. So let's open this in a new tab. Generally opens quite small. Okay, so there we go. So you can see what they're doing there. They're saying, well, we've got the height, we've got the frequency. Now divide 12 by the class width of 135 to 145. So divide by 10 and keep dividing by your class width. The next class width is 20. So do 46 divided by 20. And now you can plot all those heights of your frequency densities. Okay, and you call that axis on the left-hand side your frequency density. Okay, right. So look, this person is almost as scruffy as me. Okay, so there we go. I just wanted to append that on the end, and essentially now you can do 5E as well. There's really not too much to that. Well, they seem to have made 4 questions out of a discussion point, but okay, you can have a look at those ones. Right, so which means that next time around we're doing justification of statistical techniques, starting off with box and whisker plots. Okay, guys, well, thanks again for listening, and hope to see you back for the next one.